Here's a situation that's similar but not identical to the situation in one of your science problems. We have a target object. Okay, here's a target object at t equals 0. Okay, the target object moves at velocity, constant velocity v2. We launch a projectile from a different point at 45 degrees with some velocity that we're going to determine, so that that projectile lands on this target object when the target object gets to a certain point. And I didn't label it on here, and the labeling is kind of messed up. Let's just say that, okay, here's the this dotted line and this dotted line represent the horizontal positions of these objects. And let's just say that this distance here is S. Okay, so this is a separation of the projectile, position of the projectile and the target object at time t equals 0. Okay, how do we solve this problem? Well, I'm going to solve it using vector functions. There are other ways. It can be reasoned out in a number of ways, but hopefully we'll see something about the elegance of the vector picture. So for the projectile here, and I'm not going to go through the details of deriving this. The x of t is just going to be v naught times the cosine of 45 degrees times t. That's going to be your I component. And the j component is going to be negative 1/2 gt squared plus v naught sine 45 degrees times t. Okay, so that's the projectile. So we could say, we could put a little subscript, PROJ, on that to indicate that that's the projectile. Now, what about the target object? Well, R, the target, is what? We have an initial position, S, and a constant velocity v2, which we multiply by t, and it stays on the level ground presumably, so we have 0j. There's never any j component to this position. Okay? Now, we want these two positions to coincide. How do these two positions coincide? Well, they coincide if this equals this and this equals this. So that one of our conditions is that negative 1/2 gt squared plus v naught sine 45 degrees times t has to equal 0. And we're going to be able to, we notice we have two unknowns. We have v naught and we have t. The other condition being that v naught cosine 45 degrees times t equals s plus v2t. So now we have two equations in the two unknowns, in t, which appears here, here, and here, and here, and v naught, which is here and here. All the other parameters are presumed to be known, so it becomes straightforward to solve this equation. When I say straightforward, it's a little messy, but this equation, for example, can be solved for v naught in terms of t, or for t in terms of v naught, whichever way you want to do it, and then substituted back into this equation to get the solution. So I'm not going to go through the details of that, but you should take that as a vector picture that allows you to fairly easily set up this situation and arrive at a solution. If an object is falling vertically at constant velocity of magnitude Vy, and a vehicle is passing this object at a constant velocity of magnitude Vx, then in the horizontal direction, so the vehicle is moving in the horizontal, object is falling in the vertical direction, then from the vehicle, the object appears to have vertical velocity, in this case negative Vy, and horizontal velocity negative Vx, the way the picture's been drawn. The vehicle could be moving this way and the velocity would be positive, and I'm assuming a standard XY coordinate system. Okay? And that should be fairly obvious. If you're driving in a car in this direction, you see objects along the side of the road apparently moving in the opposite direction at the same speed that you're moving in the forward direction. So we superimpose these two velocities, we get a resultant velocity. Okay? And that resultant velocity I'll express as a vector, and it has magnitude square root of Vx squared plus Vy squared, and makes an angle here, if this angle is theta. Now theta in this case is not measured from the positive x-axis in the counterclockwise direction. Theta is just the angle within this triangle. So this angle theta that I've drawn here is the inverse tangent of Vx over Vy. Inverse tangent of the opposite side over the adjacent side. Now we could superimpose an XY coordinate system here and draw the angle around from the positive x-axis, and in that case the angle would be the arctangent of Vy over Vx, and the way this is drawn, Vx is negative, so that you'd add 180 degrees to that and you get the angle with respect to the positive x direction in the counterclockwise direction. So that works, but you have this, and this is also relevant to at least one of the problems that occurred in the problem set for Chapter 3.